The Zetasizer Pro and Ultra are the latest additions to the Zetasizer range, which combines dynamic light scattering and electrophoretic light scattering to measure the size and electrophoretic mobility, or zeta potential, of colloids, nanoparticles, polymers and proteins. Building on the strengths of the Zetasizer Nano, the new platform combines unique measurement features, hardware capabilities and software intelligence to enable novel, meaningful and robust data to be acquired quickly and easily. Using a new analysis algorithm called adaptive correlation, it is now possible to get reproducible particle-size data faster and with minimal sample preparation, leading to greater confidence in your results and decision-making. This is achieved by separating sample signal from any external noise, such as that resulting from the presence of dust or other contaminants. The Zetasizer Ultra also employs a new measurement protocol called Multi-Angle Dynamic Light Scattering, or MADLS for short. MADLS combines data from 3 measurement angles to resolve any hidden size populations and give a single particle size result that you can trust. This novel approach can also be used to determine particle concentration without the need for calibration or specific sample information. This new functionality is supported by a revolutionary new software platform, ZS Explorer, which puts the sample and the user at the heart of the measurement. It features intuitive, guided workflows that make setting up a method and performing a measurement easy and straightforward. Furthermore, once set up, methods can be easily duplicated, edited, or saved for future use, conserving valuable time and effort. The ZS Explorer software also employs an artificial intelligence-led approach to data quality assessment, which helps you get the best possible results from your sample. It subtly brings your attention to any potential measurement issues and provides clear guidance on how they might be improved. The Zetasizer Pro and Ultra find use in a wide range of industries and applications. Examples include characterizing the size and surface charge of colloids and nanoparticles, screening protein formulations for colloidal stability and the presence of aggregates, assessing the shelf life and stability of complex formulations. By combining novel measurement capabilities with advanced data analysis, the system provides a comprehensive analysis of your materials, giving you greater confidence to make your next move. The new Zetasizer Pro and Ultra. Advance with confidence. Particle characterization you can trust. For further information, visit us at www.malvernpanalytical.com.
DSC is often referred to as the gold standard technique for measuring the thermal stability of biological macromolecules. Most commonly, it is used for measuring protein stability in the biotherapeutic industry. Most biologics are proteins or protein derivatives, such as antibodies or antibody-drug conjugates or ADCs. DSC's ability to measure the thermal stability of all protein and protein derivatives is because the instrument can detect the small heats associated with the making and breaking of hydrogen bonds. These bonds are broken when the biologic is heated and it unfolds, a process which absorbs heat and is detected by the calorimeter. Most other techniques used to measure protein stability rely on monitoring the change in the environment of a particular amino acid, often a tryptophan. There are a number of problems with this approach. Firstly, not all proteins have tryptophan, and the unfolding will not be observed. It will be invisible. Secondly, even if they do have the tryptophan, those techniques will only detect changes in the local environment of those amino acids. This may not be a good representation of the unfolding of the protein as a whole. This is particularly important for multi-domain proteins. One or more of the domains may not have the tryptophan, and therefore the unfolding of a particular domain may go completely undetected. If this domain is important for the stability of the biologic, then all the data used to assess the developability of that molecule will be misleading. Of course, there are examples where spectroscopic techniques do detect unfolding of subdomains. However, it is not easy to predict or know if the data is telling the whole story or not. This unknown makes for very risky decision-making. This is why many laboratories run microcal DSC measurements to validate their spectroscopic analyses. In addition to this, the new microcal peak DSC has new smart algorithms for picking up even subtle features in DSC unfolding curves to facilitate the identification of subdomain unfolding. There are a number of other advantages of DSC over spectroscopic techniques. Firstly, microcal DSC can be used to study biologics in a broad range of buffers and formulations, which can be a problem for many other techniques. Secondly, DSC is designed to go to 130 degrees Celsius. Many spectroscopic techniques cannot be used above about 90 degrees Celsius, which means that any highly stable proteins with TMs above about 75 degrees Celsius cannot be studied. Thirdly, spectroscopic techniques are prone to artifacts from turbid solutions, inner filtering, quenching and light scattering, which plague fluorescence measurements and are often dependent on sample concentration. These phenomena can also lead to poor reproducibility. It is the high reproducibility of DSC that has led to its use in batch-to-batch studies. DSC data has been used to support a number of successful biosimilar registration applications. In addition to these advantages, the microcal DSC has low sample volume requirements and high compatibility with biological buffers. It can be run at fast scan rates, reducing experimental time, and it has features that support working in a regulated environment, including Mac software, to support 21 CFR Part 11 compliance.
So it will move to the acquisition tab as it's just done automatically, and the first thing that's actually going to happen is the auto sampler will go through a priming process, and you can see that in the bottom left there. It's telling you what's occurring with the initial wash before making the first injection, and this just ensures that the auto sampler is fully primed, full of mobile phase, and is going to make nice, highly accurate injections from the very first one. So that takes a minute or two, and you can see on the video here what's going on with the needle as it washes itself and draws through some solvent. So once the auto sampler priming has finished, you can see the message in the bottom has changed to waiting for injection trigger, and the auto sampler is now going through the injection process, drawing up sample into the injection loop. When that's ready, we'll hear the noise of the valve turning to inject the sample, and the run will start. So there it goes, initializing data acquisition, and run starts to be acquired on the screen. Now I'm just going to change the axes to our auto scale feature, so we get a nice zoomed in view of our baselines to start with, and then that will scale as the run proceeds. So we'll let those measurements go, and while they're running at an accelerated rate in the background, I want to spend a few minutes just reminding ourselves as to how size exclusion works and what the different detectors are doing, to give us a feel for the kind of information we can expect to get out of a measurement like this. So thinking about size exclusion theory then. Now, size exclusion, SEC, also known as GPC, gel permeation chromatography, is a subset of HPLC, but it's not an interaction affair at all. It relies on separation of molecules as they move through the column based on diffusion of the molecules, of the protein molecules, in and out of the pores of particles. And as they move through the column under an isocratic mobile phase, so the same continuous mobile phase, we should see a separation of our protein molecules according to their physical size. And the larger molecules come out first, elute first, while the smaller molecules elute later and later. So we should end up with a size-based separation of our different populations. And the way that works is that imagine a single gel particle within a column and a mixture of different molecules coming through. Now, as they move through the system, the molecules can diffuse in and out of the gel particles to different extents. The larger ones, like the triangle, are excluded from many and move faster. The squares get in a bit deeper, and the little spheres get in much deeper all the way to the center. And as the molecules move from particle to particle to particle, so the separation between them grows and grows and grows until our individual populations are separated. Now when the sample elutes, we're going to measure it with one or more detectors, and what we're doing with OmniSec is measuring a whole range of different detectors to get as much information as possible. So our multi-detector SEC separation involves a standard kind of chromatography setup with degasser, pump, auto sampler and column oven, and then the samples flow through a range of detectors, starting with refractive index, moving through to a UV-Vis PDA, a light scattering detector, and an intrinsic viscometer. So let's start with refractive index. We all know that when we dissolve something into a liquid, it changes the refractive index of the solution, the way the light bends as it passes through. And this response is directly related to concentration, so we can use the RI detector as a very sensitive concentration detector for just about any sample we want to measure. The next detector in the sequence is a UV-Vis PDA, which of course we use to measure UV absorbance of anything with a chromophore, and obviously proteins are very strong UV absorbers, so we can use this as a second concentration detector. We typically use RI as the primary one because it removes any questions of molar extinction coefficients and UV absorbance differences between samples, but it's nice to have both because there are occasions where you want to measure conjugates, for instance, so a protein conjugated with polysaccharides or a PEG or membrane protein detergent from a membrane protein application. And so two concentration detectors with the RI and the UV. The next detector is a light scattering detector, which of course we use to measure molecular weight. So when you shine a laser on your molecule of interest, it scatters light, and that light scattering intensity is directly related to the molar mass, the molecular weight of the sample, according to the Rayleigh equation. And so by using a light scattering detector, we can directly measure the absolute molecular weight of our protein, regardless of its structure or where it elutes from the column, anything like that. We get a direct and accurate molecular weight measurement. So the final detector is a viscometer, which is a measurement of molecular structure. And just to keep this nice and simple, it's the inverse of molecular density. So we imagine a protein being a very high density, in most cases, globular compact molecule, and a high density is a low intrinsic viscosity. On the other hand, a more extended, open, fibrous molecule will have a higher intrinsic viscosity and a lower density. So a viscometer is a way to differentiate the two molecules in the image there, that sphere and the string of spaghetti, if they're the same molecular weight. So the light scattering would see the same molecular weight, but we can use viscosity to distinguish structures. And I'll show you how that can relate to proteins and protein aggregates right at the very end of the presentation. So just to summarize that then, what are we doing? We have light scattering detectors, refractive index, UV absorbance detectors, and a viscosity detector, and those are the signals that we're measuring. We combine those, in the case of the concentration detectors, to maybe measure a bit of compositional information, such as with proteins and PEG conjugates, and we can use those to measure the sample concentration. Sample concentration combined with light scattering intensity gives us molecular weight, which is the thing we're most interested in, and to a lesser extent for proteins because they're generally too small to measure, but the radius of gyration as well. Maybe that comes into play with some very large aggregates. And then on the other side, combine concentration with viscosity, and you can measure this property of intrinsic viscosity, this measure of density. But more interesting maybe than intrinsic viscosity is that you can combine that with molecular weight to calculate hydrodynamic radius as well. So by combining the two, we can actually get a physical size measurement. And all of these parameters and measurements come out of that one single SEC run. And then I will do that for the individual peaks as well. So we'll just select the, I'm actually going to select 4. These 3 peaks are quite well resolved. And then this fourth one, I'm just going to take all these aggregates and treat them as one individual peak. Now the software's been analyzing in the background every time I put a peak down, and you can see the results here. On the derived data, we see where our molecular weight trace cuts across the refractive index chromatogram. If I zoom in a bit, then we can see really beautiful, stable molecular weights across the monomer, dimer, and trimer peaks, indicating that these are nice, pure, monodisperse populations. And then in that last long one, the aggregate peak, we've just got a broad range of molecular weights stretching up into millions and above. And that data is, the numerical results are presented in this table down here. So you can see we've got a measured molecular weight of 66 kilodaltons for the monomer, 134 for the dimer, 205 for the trimer. So all of these are exactly where we would expect them to be for our BSA monomer, dimer, trimer. Our MW over MN value is polydispersity, and a value close to 1 indicates that these peaks are absolutely pure. So these tell us that these are monomer, dimer, and pure trimer in those peaks. The fourth peak has a higher molecular weight and a wider range of molecular weights, as indicated by that MW over MN number there, and this tells us that this is a broad range of poorly resolved aggregates. We can also look at intrinsic viscosity, which is a measure of structure, and that gives us hydrodynamic radius, which is what we're more likely to be interested in. So we can see our monomer peak, 3.5 nanometers, 4.9 for the dimer, 5.9 for the trimer, and then 8 and up, in fact, for the aggregates. It tells us that our fraction of samples, our monomer is about 75% of the sample, 15% dimer, 5 trimer, and then about 5% of those larger aggregates. And then we have our measured recovery and concentration there as well. The recovery is not quite 100%, and that's just because I've cut off the bottom corners of these peaks, so it's just a little bit not taken into account. But overall, you can see we've got a really nice, comprehensive characterization of our BSA, and our results are really nice and accurate. So I'm going to move on and analyze a couple of IgG samples, and then we'll look at the heated IgG as well. So I just click on the next IgG. Do I want to save my results? Yes, so that I can come back to them later. And after a second, we move on to our IgG sample. It looks very similar, with some primary peaks and then some aggregates. There are actually shortcut keys for setting in baselines and limits, so I'm going to use those. And again, I'm going to call all the aggregates together. Then the second peak. Then the third peak. And again, in our molecular weights, 2 really nice monodispersed stable populations, and then the aggregates more varied in their molecular weight and higher up. So you can see I've got about 145, 150 kilodaltons for the IgG monomer, 300 kilodaltons immediately identifies the other one as a dimer, making up about 90 and 9% of the sample, respectively. And then just a couple of percent, just 1% in fact, of these higher molecular weight aggregates, which are in fact up at 2 million or more. So very high molecular weight aggregates in there. Size-wise, measuring 5 nanometers for the IgG monomer and about 7.5 for the dimer. Again, perfect measurement of the RH there. So what I'm going to do is run through a couple of these, keep going with a few more of these samples. So we'll save those results and move on. And again, set baselines, zoom into the sample, and analyze those peaks. Now I'm not quite happy with my intrinsic viscosity baseline there, so I'm just going to drop that down a bit. I can pick up any one of these baseline points and move it to wherever I please, so obviously we can make it go silly, or I can just lower it down a bit more to what I think is a more appropriate baseline value there. And again, very similar results there, so let's move on to our heated IgG sample. Now this, you can see, looks quite different. There's this third very large peak in the light scattering, and of course we know this is going to be some more aggregates that we've created by heating up our sample. So I'm going to go through the same routine though, just to keep everything consistent. And again, 3 nice peaks, stable molecular weights, and then increasing in the aggregates. A couple of things to note: our dimer molecular weight is actually slightly higher now, and that's because these aggregates are starting to dominate and they're not well resolved from the dimer peak. So a little bit of an increase there, but that's not a problem. The aggregate molecular weight, actually around 2 million, is not changed too much. It's actually a slight decrease from what we were looking at before, but of course the fraction of sample is much higher. These are now nearly 5% of the sample instead of being just 1% as they were previously. So then the fourth and final IgG, we'll set baselines and limits over those again. And pretty similar results. So very nice. Now once I've saved those, what I want to show is how we can compare samples and overlay them and really get a feel for how the IgG sample has changed. So I'm going to maximize this view and I'm going to change it to the overlay view. And then just by selecting multiple injections in the record view there, I can bring in all those injections into a single chromatogram. I'll baseline subtract them, so we're looking at the kind of them all overlaid very nicely, and here we can very nicely see the difference. If I zoom in here, we're looking at the RI trace here, by the way, and you can see in the red and purple sample, the initial sample, we had our monomer and dimer, and then just a small amount of larger aggregates. But then in the black and green, the heated sample, you can see we've got this growing population of aggregates there. If I switch to the RALS detector, the light scattering detector, then you can see that difference very dramatically in the presence of those large aggregates, which of course scatter so much light. So we get a very nice visual representation, both of the precision, the repeatability of the couple of duplicate injections, which are nice and consistent, and then the difference between the raw and the heated samples. So it's a really nice, quick way to compare samples. Now, additionally, the results table has been updated to incorporate all the data from those samples. So I'll run through that. If we just selected the one, then we just have our peaks 1, 2, and 3 for our one injection. If I select the 2 IgG samples, then you can see this table updates, and now we can see 145 kilodaltons for both, just about 300 kilodaltons for both, and then 2.5, 2.75 million daltons for the aggregates. And in fact, the software will calculate statistics for both of these automatically. So we can see we've got just for the monomer and the dimer molecular weights, just a couple of percent or less, in fact, in the monomer case, of variation there. A little bit more in the aggregates. They're going to be a bit more variable because of their small amounts really within the sample. And so we can see that for the molecular weight, we can see that for the intrinsic viscosity, and for the RH, which again, just a few percent variation in there, telling us that we've got really nice repeatable results between those samples. Of course, if I add in the 2 heated injections, then we can see any additional variability that might be coming in. For instance, the aggregate molecular weight is becoming a bit more variable. And also the fraction of sample, we can see that it's gone up from 1 to 2% in the initial samples to about 5% in the aggregated samples. So very significant differences and very easy to visualize and see. Of course, these tables can be copied out to another software package, and they're fully customizable as well, so you can just look at the information you want. So the last thing I want to do is analyze these couple of pepsin samples and compare those to the IgG. So I'll quickly, as before, set some baselines and limits. And you can see that for the multiple samples, this can be done so quickly. just flicking between samples, setting baselines and limits, and then immediately analysing them. So in our pepsin here, actually the centre peak is our monomer, about 38 kilodaltons, very close to the expected molecular weight, and then we've got some degradation products, at lower molecular weight, and some aggregates at high molecular weight. And I will do the last sample as well, and then we will compare this with the aggregated IgG samples. And there we go. Again, monomer, degradation products, and the aggregates. So what I want to do now is overlay those samples briefly and compare the intrinsic viscosity signals for them. If I go to the overlay view, so this is RRI. If I look at the viscometer signal, then you can see the viscometer signal for the aggregates in the pepsin, and indeed the monomer, is far, far higher than the IgG, and that's because these samples have these proteins have different structures to each other. Now if we look at the numerical data, and we're only interested in peak 1s here, so peak 1 for the heated IgG has a viscosity of about 0.15 and a size of 16 nanometers for about a 2 megadalton aggregate. Likewise, 2 megadaltons for the second one, and 16 nanometers, 0.15. So really nice repeats there. Now the pepsin aggregates are about 2.2 megadaltons as well. So they're similar molecular weight, but their intrinsic viscosity is 1.4, 1.5. So it's 10 times higher than that of the IgG. And that feeds into a hydrodynamic radius of 40 nanometers, 39, 40 nanometers in size compared to the 16 nanometers of the IgG. So what this tells us is there are big differences in the structures of our aggregates between the pepsin and the IgG. The IgG is a much more compact globular structure, whereas the pepsin is a much more extended and open structure, possibly a fibrous aggregate, something like that. So not only can we characterize fully the samples for their different populations and the molecular weights of those populations, but we can also investigate their aggregation state, the molecular weight of the aggregates, and also then even to some extent the structure of the aggregates. So a very nice demonstration of kind of all of the data that you can get.
Thank you for listening. For more information, please visit www.malvern.com.
Welcome to the lab. Today I'm going to be giving you a short demo of the new Nanosite Pro. So I'm Jake Austin and I work here on the product development team, and I'm really excited to show you what it can do. So Nanosite Pro is quick, easy and accurate, which you're going to see shortly, and I'm going to start off by showing you how we load a sample. So to start off with, we're going to be talking about the hardware side of it. So we have our laser module here. It's got a nice new grip on it, which is very ergonomic, makes it easy to hold. Then inside we have the bits we need to put on. So we've got a holder inside the instrument for the low volume flow cell. So we can now put this on top using these guides. Then we've got our screws as well, can be held in the instrument. We just screw these in, secure the flow cell to the laser module. So it's 2 in each opposite corner. And then once we've got our screws in, we can now put in the inlet tube for which the sample will go into the measurement window through. And then finally, our outlet tube for which the waste will go out through. Now our laser module is ready for the sample to go into it. So we do this using a syringe. So this sample we've got today is some exosomes that have come from urine. So just going to load these in slowly. So now we can put the laser module into the instrument. We do this by just putting it inside this new ramp, which makes it slide in easily into the guiding rails, and it then locks into place. And then we just put our tubing into the catch, close the door, and now the syringe goes into the syringe pumps. We just need to adjust that, put the syringe down, and then lock it in place. Now that we've finished setting up the sample, it's all ready to measure and we can move on to the software. We start off on the home page. So here we can look at things such as the instrument status, check that things are connected properly. We can look at our favourite projects and experiments, and also we can get news and updates from Malvern Analytical. Where we set up our measurements is in the measure page. So here is where we can set up our measurements and capture them. So if we start the camera, immediately we should see our particles. So here we can see these sort of dots dancing around on the screen, and each one of these represents a particle. So they're undergoing Brownian motion, which is what's causing them to move around in random movements. And each one you can see is various different sort of sizes. And this pretty much correlates to what size they are in your sample. So to get a quick idea of how the size might be for your sample, you can click on the preview overlay. This gives you a very quick graph, get an idea of what the size population might be. And once you're happy with that, you can then look at actually setting up your measurement normally. So what you can do here is you can do it one of two ways. You can either do it using manual setup, or you can do auto setup, which is much easier to do. So we're going to start off here by using the autofocus. So I just click on this, and then the software will look for the best focus for this sample. So the software has now found an optimum setting for the focus. So now we can look at setting up the rest of the measurement. So what you might do to find this easier is to get the sample flowing. So now I'm going to start off the syringe pump at a high flow. So we just turn it on here and then click the 200. And once that gets going, we can then slow it down and just make sure we get a slower, steady flow to make sure we can track this Brownian motion of the particles. So now that we've got the flow going, we can actually set up the measurements. So we start off by doing this by giving it a name. So what our sample is here is exosomes, so I'm just going to call it that. And these exosomes have actually been labelled with a membrane dye, which allows us to do fluorescence measurement. So we can create this here, and what this gives us is a new measurement which already has the scatter and fluorescence parts built in. So for the scatter part, to set this up, we've already got our settings here, so we can just click Apply Current Settings, which gives us them all over here. And I'm just going to lower the number of captures to keep the measurement shorter for this demo. And then the fluorescence part, which we've not actually shown how you can do that yet, I'm just going to show now. So what we can first do is apply our filter. You can see now you can't see the particles. But when I increase the exposure and contrast to make it brighter, you should start to see them come through here. Might just make the screen a little bit brighter as well to help see them better for this. And then again, now that we're happy with those settings, we can again click Apply Current Settings, puts them all in here. Now we're just going to change our number of captures down to 3, and then we can click play, and then the measurement will run. As well before that point, but now it's going to start capturing. So you see this green progress bar going along, and it will go through 3 of those captures. And each time in between the captures, it flushes sample through, ensuring that the sample's not going to be photo bleaching during the measurement. And then once this sample has finished all 3 captures, it will then move on to the fluorescence part. And then it will start off with the camera off, because again, we want to avoid photo bleaching, so the camera won't be on, so we avoid disturbing our sample. And it's going to run the measurement. And when it captures, again, what it'll do in between each capture is it will turn off the camera, again to avoid that photo bleaching and making sure we're going to get a good fluorescence measurement so we can compare well to our scatter part. Because once these are both done, the software will automatically overlay those 2 parts of the measurement and make it easy for the user. So now that measurement's finished, the processing will be happening in the background, and what that means is we can either look at other data in the software that we've measured before, or we can run a different sample. But for the sake of this, we'll just be using the same one, so I can just start the camera again, create a new sample, and just run a scatter measurement this time, so I can just apply our current settings and click go. Once our measurement is finished processing, the Analyze page, we can quickly see what our results are. So here we've got our exosome measurement we did earlier, and we've got an overlay of the 2 results. We've got the scatter part and the fluorescence part, and you can compare those 2 distributions straight away. We've also got a fluorescence efficiency value, which gives you a good idea of the ratio between those 2 measurements. We can also look at other things separately, so what the size values are, such as the mode and mean for each one, and we can switch between them. We can then also look at the tracks for these videos. So for example, here we've got the size, the scatter tracks for the exosomes, and we can play through them and have a look at what they look like. We can also compare 2 results. So we've got an exosome measurement we did earlier today, and we can overlay those 2 and have a look at how repeatable they have. So here we've got some nice repeatability, overlay really nicely. And we've also got our quality page. So here we can look at things like our data quality guidance, giving us an idea of if we've got any possible issues with the measurement, if there's anything we do to improve them. And then finally, we've got our report page where we can customize a report and use it to print it off as a PDF. And that's the end of the demo. I really hope today you've been able to see how quick, easy and accurate the new Nanosite Pro is, and I really hope you've enjoyed it. Today we've looked at exosomes, but it's also really versatile and can be used for other nanoparticles and bioparticles, such as nanobubbles, lipid nanoparticles and viruses. And if you have interest in any of these applications, then please contact your Malvern Analytical representative.